Hey guys, it's August here. Thanks for checking out this video on celestial navigation. This is a replay of a live stream that me and Andy did on Crowdcast, and we talk about the history and philosophy of celestial navigation, and we get to just skim the surface of the technical side of this. If you want to learn how to do celestial all the way by yourself, the whole shabam, we're going to have a virtual workshop coming up soon. It's going to be live, fully interactive, tons of fun, and it's half price from a regular celestial workshop. So check that out in the description below, and I hope to see you there. So thanks for your attention, and please enjoy the show.
Ahoy sailors, welcome back to 59 North Live. I'm Andy and that's August, and this is the Storm Weather Shanty Choir as usual playing us in. So nice to see you again, August. I'm looking forward to doing one of these in person with you sometime when all this craziness ends.
Yeah, same. I mean, this is something that's close to our hearts, and I've been looking forward to this a lot. I think it's going to be a lot of fun. So, I'm excited. Hey, everyone.
Yeah, well, welcome, guys. We're going to talk about Celestial Nav today. We've got sort of part history, part technical discussion that we're going to walk you through here. You won't know how to take a site and reduce it by the end of this, but you will if you do one of our other workshops, which I think we're considering doing one online at some point. But I'll just explain quickly how this is going to work, and then I'm going to hand it over to August to talk about some history of Celestial Nav and why we kind of have what we have today and where it all came from. So if you guys have seen us in Crowdcast before, you'll know how this works. If you haven't, at the bottom of the screen underneath August and I, you'll see a button that says Ask a Question. So if you have a question to ask it there now, and we'll get to that as we do the Q&A, probably throughout the talk and then at the end for sure. We expect the content portion of this to go for about an hour, and then we'll have about 30 minutes of Q&A afterwards. So 90 minutes if you stay for the full show, thereabouts. If you want to come up on screen as well, we can do that. So as you ask a question, I can invite you up on screen. You guys can talk to us in person, and we'll do that if we have time for it. Also, remember, we're doing these for free, and we're all unemployed at the moment. So if you guys feel like you learned something or got some entertainment value out of this, consider kicking us a little few dollars for our quarantine beer fund, and you can do that also at the bottom of the screen. I'll put up one of those prompts every now and then throughout the talk today. No pressure, but if you have some expendable income and want to support what we're doing, we'd really appreciate it. Keep these live sessions free, and we have fun doing them. So thank you guys that have donated, and I think we'll have, as long as we're in quarantine, we're going to do these live sessions, so we'll see how it goes from here. All right, so August, why do we do this? You and I are both passionate about celestial, at least in the philosophy and the theoretical side of it. So what's in it for you?
Yeah, I mean, it's a good question, isn't it? Because it's basically now with GPS, it's just so cheap and so easy to find your position anywhere, just using that. But I just really love the one is the historical part of it, just to learn it and like how this was done back in the good old days, and it's also, it just feels really good to know that even if every electronic fails on your boat, that you are going to be able to make it to land, sort of just with your with only your skills and the stars above you, really. And I sort of got into it through astronomy, actually. I'm really into astronomy. I love that, and I've telescopes and I can observe the stars and the planets, and I love that. But through celestial, you kind of get to interact with them, and I think that's sort of brings it to a whole other level. So
Yeah, I like to say too, unless you're sailing or working on ships professionally, you don't need to know celestial. That said, like for what we do, for the big boat that's got the British flag, the skippers on that boat have to have a Yachtmaster Oceans endorsement, and that Oceans license is celestial. So you have to understand celestial and know how to do it in order to get the license for that. But that's a professional qualification. Most recreational sailors are never going to need it. I mean, take time next time you go on your boat and count how many devices on board have a GPS in them. I mean, people's watches, it's just ridiculous. Cameras now and stuff, which is interesting. Looking as an aside, looking at the rules for the OGR we're doing in a couple years, how strict they are with what devices have GPS on them. I mean, drones, for example, you can't operate a drone without a GPS in it. I mean, you can, but it's much more difficult to fly. So it is a bit crazy how easy it is to navigate, like you said. But when I teach Celestial and we do this talk, part of the talk I'm going to give later on today is exactly what I do on the boat when we have crew and we're at sea. It's just a cool thing to know. It's a neat way to stay connected to sailing history and that red thread from navigating from back in the Polynesian days to now. And it's something that's really fun to do offshore. You get a nice calm passage, and you, besides reading your book or listening to a podcast or whatever, getting out the sextant and actually practicing Celestial offshore is a great way to pass the time. And I know you've pulled out the sextant and showed it to crew on Eastbjorn, the couple of passages you've done.
Yeah, I've had it out on every single one. I think it's it's just really fun. It's a great sort of little also a little history lesson, and I think like maybe you won't, like, celestial navigation won't be actually necessary ever again, but I do think that your understanding of the globe and sort of rumline navigation and latitude and longitude, I do think that if you know how to do celestial, you understand that a bit better. So
you took the words out of my mouth. I was going to say the same thing, and I even think it's less than that. You don't even have to know how to do celestial. You have to understand some of the concepts about how I got my globe in the background. I'm going to be using that as a prop later on. I'm going to get all excited about this. My hands are flailing around. But by understanding some of the sort of spatial awareness concepts that are required to actually do celestial, you don't actually have to know how to reduce a site to use those concepts, even in daily life. Like, I find myself challenging myself when I'm driving around in the car. If I lose track of the directions or something, I'll be like, I can find my way back. Or if I'm out for a run in a new place, I tend to like kind of run out and then find my way back via a different route. And you're literally using the direction to the sun and shadows and this kind of stuff. And that kind of is natural navigation, which is another part of this. There's a great guy, a couple books written by a guy called Tristan Gooley. I'll write his name down here. But if you look up Tristan Gooley, he has some really cool stuff on natural navigation, which celestial, the foundation of celestial is understanding your place both on the surface of the earth, but in relation to the rest of the universe. And that's probably the most practically useful part that you'll learn from it, because you don't ever need it, like you said.
Yeah, that's right.
So how do we get here, August? You want to enlighten us with some of the history of this? Because it is a really fascinating kind of background, especially when we get up to the John Harrison, the clock era and that stuff. I love telling that story, but I'll let you do it this time.
All right, cool. Hey, just jump in if you feel like it. If I'm glossing
over
something.
I have a couple anecdotes from my interview with Robin Knox Johnson, which we'll get to. I got some audio to play for you guys for that, but I'll let you get us started.
Cool. Yeah. So if you look at the whole sort of era, the whole span of time that people have been sailing the oceans, celestial navigation, how we know it today with our sextants and tables and that, is a pretty sort of short little bit at the very end. It's fairly modern tech, and back in the like thousands of years ago, when people first started sailing, they would use coastal navigation and look at cliffs and islands and that sort of thing to determine their precision. And then when you head further offshore, of course you can't see them anymore, and you have to rely on the stars and the sun, and that it's very difficult. Let's see, I got my own globe prop right here, because the Earth is spinning around. That makes celestial navigation hard. If it was stationary, then every star in the sky would just be a lighthouse. We would always know where they were, but because it is spinning around, we need maths and tables to figure out where we are from them. There is, however, one star that does not move, and that is Polaris, located very conveniently just above the North Pole. And so that makes it still in the sky whenever the Earth is spinning around. that is always sitting above the North Pole. And that was used extensively by the ancient mariners to find their way across the oceans. It was a really big part of how the Vikings sailed across all the way to America over 1,000 years ago. They would use that as their basically just a giant compass needle in the sky to find their way. And they were sort of being limited to that. They always used a lot of natural navigation, just like you talked about, Andy. They would sort of know the feeding grounds of the different seabirds, and they would navigate from that. They would know how the ice was moving around in the area. And one really cool thing that they did was to bring ravens with them on the longships, and they would release a raven. The raven would fly up into the sky, and to get a really good view. And if the raven saw land, it would head for the land. And then the boat could follow or turn the other way if that was a scary thing. So pretty sort of cool way to
awesome.
Navigate before we...
So I have two links I want to just point out while you're talking. That concept of the way the Vikings navigated and the Polynesians in a similar sense in the South Pacific. There's a link right underneath August's head called We the Navigators by David Lewis. That was a book where he went and spent time with the Polynesian navigators back in the 60s and wrote about it. It's a pretty scientific book, but it goes into very much detail about what you're talking about. And then in the chat, there's another book called Vinland Voyage, which is a book from another book from the 60s. This group of British guys had this wooden sailboat, and they wanted to retrace Leif Erikson's route across the Atlantic to try to figure out where this mythical Vinland was, because people had theorized it was Newfoundland, Nova Scotia, Cape Cod, all these different places. So they retraced the voyage, and it's like a classic kind of seafaring book, but each chapter alternates between kind of their own adventure and then what Leif Erikson was doing back in his day and hypothesizing all this stuff. And an interesting fact about David Lewis, I don't know if you knew this, August, but David Lewis was a sailor and a scientist, Australian guy. He had a wooden ketch called Eastbjorn that he sailed back in the day, and he also later had a steel boat called Icebird, which is another book of his. Went single-handed around Antarctica back in the 60s or 70s sometime. But I really liked his books and thought, oh, Eastbjorn's a cool name for a boat. And that is kind of where the name Eastbjorn came from.
I don't
know if you can still hear me, August. You froze on the screen. Are you still there, August?
Can any of you guys
okay, we lost August. I'm going to close him out and bring him back up again. So, guys, like I said, there's a couple links there. And Dan K just suggested we look into another one here. If somebody in the chat can just confirm, can you guys still hear me? And is August frozen for you guys as well? Okay, Heather. Okay, cool. You guys can hear me. All right. Sorry about that. So let's see what happened to August, and we can get August back here. Okay, waiting for August to reconnect. All right, cool. So anyway, I was telling August about David Lewis. So I said at the bottom, there's a link at the bottom to We the Navigators, and then David Lewis wrote another book called Icebird, which I'll write in the chat here, and then that Vinland Voyage. So some really interesting kind of pre-celestial navigation that we had there. And let's see if we can get August back up here. Stand by, guys. All right. This is the most frustrating thing about doing these live sessions, really. It's like, if we could be here in person with you guys, this would be much smoother. So thanks for your patience as we try to deal with this technology. It's pretty cool that we can use it, but it is frustrating sometimes when it does this. Somebody asked, let's take a question here while we're at it, actually. Somebody asked, let's see. There was a question here from David. David asked, have you ever used Celestial Nav in anger? And yes, in fact, I have not because we had to, but rather because I wanted to see if I could do it. So in 2017, and I'm going to put this video in a link here at the bottom of the page, but in 2017, we sailed Eastbjorn from BVI to Bermuda using only Celestial Nav, and it was the first time we took Eastbjorn across the Atlantic. And we made a little 15-minute video of it on YouTube, but that gives you an idea of what it's actually like to navigate with Celestial. And we did it for real. The only GPS information we had on the boat was Mia was keeping a GPS log sort of secretly, just writing down the numbers, because we thought, well, we got paying crew on the boat. If we have an emergency, we should know where we are so we can call the Coast Guard or whatever. But otherwise, the rest of the crew, and even Mia, didn't plot those positions. They were just numbers on a piece of paper. But we used it, and we navigated all the way to Bermuda. And I'll tell you what, it was extremely satisfying making landfall where we thought Bermuda would be on Celestial. And it was exciting because it proved that, all this study and all this stuff that I've done, I've taught a bunch of these workshops. I really like the theory behind it. But it's another thing altogether to actually use it and have that uncertainty, because when you're practicing Celestial, you have the GPS position right next to you where you can, hey, August.
Hey, sorry
you have
about
the
that.
GPS position right next to you. I'm just explaining using it in anger. You have the GPS position right next to you, but when you're navigating by Celestial, you don't have that reassurance that you can just look at the GPS and find out where you are. You really don't know if Celestial is working until you get to where you're going, and if that island appears where it should appear, it's like, oh yeah, I was doing this right all along. Now, once you get comfortable with Celestial, you trust it. You have to trust it. If you don't trust your sextant sites, you're lost. So it's required that you get really comfortable using the sextant and practicing with it, so that when you turn the GPS off, you're confident doing it. So, cool, August. I just took a couple questions there while you were off in the ether. So I'll let you pick it back up. I'm done telling my David Lewis story. So here we go.
Okay, cool. Yeah, thanks for filling in there. Yeah, so about, we mentioned the Polynesians, which of course are located in the South Pacific, and they do not have an equivalent to the North Star as we do in the Northern Hemisphere, unfortunately. That is sort of just a void up in the celestial South Pole. But they did develop some really, really cool ways of natural navigation, where they would just observe the water, and from how the waves were acting, they could tell how the islands around was interfering in the water, and were able to determine where land was based on that. And it is really, really amazing. So you should all go read that book. As we sort of developed into the, I guess, more modern age, and started to understand more about how the Earth was spinning around, how the solar system worked, the basis for offshore navigation was what we call latitude navigation, based on noon sights of the sun, really, where people would, every day at noon, when the sun is at the highest point in the sky, they would observe the height of the sun, and in reference to the horizon, and then use that to determine their latitude. And the higher the sun was in the sky, the further south they were, and the lower the sun was in the horizon, the further north they were. And it's a really great idea. It's pretty easy to pull off. You don't need a lot of maths, and you don't need a lot of fancy timepieces to pull that off. The big problem with it is that you only get your latitude from that. And as people were crossing the oceans, crossing the Atlantic, for instance, they would know their latitude precisely. And they could maybe say, like, if you wanted to go to Cuba from Europe, you would just sail south until you hit like 20 degrees north, and then use those daily observations of the sun to stay at 20 degrees north. Or you could use the natural navigation way of doing that, which is sailing south until the butter melts, right?
Well, that concept, you've probably heard the phrase "running down your latitude." That's literally what that was.
Exactly, yeah. And so that's all well and good. You're able to stay on your latitude very precisely. The problem with this is that you have no idea of your longitude, so you just don't know how far west you are. And a lot of ships were wrecked this way because people would try to keep track of their longitude by dead reckoning, which is basically trying to calculate how far you've sailed based on your speed and your course. And if you're doing a long voyage, the errors, that really piles up and accumulates because of currents and just the inherent difficulty of keeping track of that. And it would not be weird for ships to to arrive on the other side a week before they expected, running aground on the rocks. They had no nav lights, they had no radar, they had nothing. So a lot of ships were lost that way, and the nations of Europe were getting pretty desperate to figure out this longitude problem. And the reason why longitude is so hard to figure out, basically, is that because the Earth spins around this axis about the poles, if the sun is over here, or the star, or whatever, it's the latitude of that point just below that object. It doesn't change very much. Like the point just below the sun, for instance, it changes from the equator to the Tropic of Capricorn up here and back, and that takes 6 months for that journey right there. But the sun moves longitudinally around the whole 360 degrees of the Earth every 24 hours. And that is why you need to know your exact time to figure out your longitude. And that's not an easy thing to do if you're on a ship in the 15th century, where the only timepiece that exists are pendulum clocks that weighs hundreds of pounds on shore. Because you can't bring those on a ship, because as the boat is rolling around, that pendulum is just gonna come hurt people and not work the way it's supposed to do. And also the clocks back then were really susceptible to temperature changes, and humidity would really mess them up. So there was no real way to keep time back then. But all these nations of Europe, they came up with these enormous rewards to anyone who could solve this longitude problem, and all these there's so many crazy schemes that would figure out to try to solve this, because anyone who did would become like a massive millionaire in today's currency. There's a really good book about this called Longitude, that I think we've read a couple times between us, Andy.
Absolutely. I just put the link in the chat there. Yeah, it's a really good book. And I think there was a short BBC documentary that you might be able to find. I'll see if I can find it on YouTube. A little documentary about longitude that is kind of the book in video format. But yeah, great book. Highly recommend that.
Really cool, yeah. And so there were basically two sort of schools of figuring out this problem. One was the mechanical approach of actually constructing a clock that could keep time well enough to be able to go to sea. And George Harrison eventually
John Harrison,
made a chronometer.
Not the Beatles guy.
What's that?
John Harrison, not George Harrison. George Harrison is in the Beatles.
Oh, right. That's right, John. And so he eventually actually won that prize. The other way to do that was a very clever way by the sort of astronomy school, and their idea was to turn the entire night sky into a giant clock, by mapping all the stars and the trajectory of the moon. They would sort of turn all the stars into the numbers on a clock face and have the moon be sort of the hand that moved across the sky. And so the mariners would be able to tell time by the moon's proximity to these stars. And it took them decades and decades of hard work to map all these stars and the moon's motions, and it really almost makes GPS looks easy to figure out. So that's a very, very cool thing they did, and that method too worked in the end. They figured out, and it's a proper way to find your longitude, and it was popular in sort of the first half of the 18th century, where the chronometers that it was kind of racing were still very bulky and very expensive. People would do lunar observations, but in the end, people would rather buy chronometers as they got cheaper and lighter, just more accessible. So yeah, eventually we got there. And,
So, August, I have a little aside here that one of my crew members told us, and we could go on for 3 hours. I realize we got to keep this moving, but
right.
because the same problem with the time issue happened later in the 1800s when America was working west and building the railroads, because you'd have these long stretches of railroad track. And my friend Rob Miller, who sailed with us on Eastbjorn and I have since become friends with, told me this story. When I was giving my celestial spiel on the boat when he was on board, he's like, hey, I got a story for you, because he's a clock guy. He restores old clocks. So he's like, they built these tracks out to the west, and there's just one long stretch of tracks. So trains going east and west would have to pass each other on different sidings so they didn't head-on collide. And if I'm on train A and you're on train B, and if our watches aren't in sync, we can't plan when to pull off on the siding to pass each other safely. So around the same time the telegraph was invented, the U.S. government commissioned the Hamilton Watch Company to create a pocket watch that was accurate enough that train conductors could synchronize their watches to avoid all these head-to-head train accidents. And Rob was telling me this story, and I was like, I have to have one of those. And he ended up getting me one. I think I bought it from him, but he restored it for me. And it basically is a pocket watch that doesn't have a cover on it, so it's easily visible as soon as you pull it out of your pocket. And it was such that it had to be within a certain degree of accuracy that was dictated by the government so that we could synchronize our watches as train conductors. So it was another instance where time was like super important to commerce.
Yeah, that is really cool. You showed me that clock. That was pretty epic.
Yeah, it's really neat.
Really
A little
neat.
mechanical wind up clock. It's really cool.
Yeah. Okay, so I'm gonna go ahead and sort of, because it wasn't only the science and the mechanicals of the watches that developed through this phase. It was also the tools of which we used to measure these angles with. And today that is known as the Nautical Sexton right here. This is basically just an advanced angle measuring tool, really. And the way this works is that I look through this telescope, and my view here is split through this in this circle right here, which consists of half of it's just glass. So as I look through this, I see the horizon just in front of me, and the other half is a mirror which reflects whatever is in this mirror up here, which is the index mirror. And if I move this, what's called the index arm, I can change the angle of that mirror, and so I can get my celestial object to reflect here back into this mirror, and so that I can bring both the horizon and, say, the star into the same field of view. So I can aim that out there, and I can adjust this, and then when I'm sort of in the ballpark, I can release this clamp, and I can finely adjust it with this micrometer drum down here. So that's the very far, there's a worm gear on the back here, so I can get some really fine adjustments to that. And I would look through there, and when I'm confident that the object and the horizon are lined up perfectly, I will call Mark to Andy, for instance, who's standing by with a clock, and he would get the exact time of the sighting, and then we can read off the actual sight here. We have the degrees on this arc right here, and then we have on the micrometer drum, we have the minutes right there. This particular model has a really neat little looking glass where you can swing back and forth. It's really really cool. This particular model is so your question there, Ben. This is a Russian. It's called a Snow M Sexton. It's a really common sextant here in Scandinavia because the Russians produced a lot of these. But every sextant is very similar to this. They have some different features, but they all, if you can use one of these, you can use all of them. Also very important, these things right here are shades that you can swing in front of in this case in front of the horizon, but and more importantly, you have these shades that you can swing in front of the index mirror, because you're going to be looking at the sun through a telescope using this, and you really need to put some shades in place there for that. So
and they say, aiming, you call it shooting the sun or shooting the stars, and it is, the terminology sounds like a gun, and it is the same thing. The more you practice with it, the more accurate you're going to get, because it's hard enough to see the sun in the viewfinder when you're standing on a fixed dock on a pier looking over the ocean, let alone on a boat on a calm sea, and then a boat on a rough sea. It does definitely take some practice, but it's not complicated to use as a tool.
Yeah, you're absolutely right. Absolutely right. So this is really cool, but again, this is really kind of advanced celestial technology, and we did certainly not start out this way, because this is a very derived instrument. Back when people were doing like the first ocean crossings using latitude navigations, they were using very much cruder instruments. And I actually put together one of the first tools that people used to sail across oceans were called cross staffs. Super basic stuff, crude enough that I just put this together in my garage in about 30 minutes for this. And this was what they used back in. Some people think these were developed around the birth of Christ, the first models of this. And the way this works is that I will put this pole right underneath my eye, and I would move this cross piece back and forth and I'll aim it so that the celestial object is in line with this point up here on top, and the horizon is it's lined up with this bottom part. So I would look at the horizon like this and try to line up the horizon down there and the celestial object up there. Now this is very inaccurate for a lot of reasons, and I actually learned a lot just playing around with this and making this. And one of the things that makes it very, very difficult is that with the sextant, because you have these mirrors, you actually have the horizon and the object in the same field of view through that telescope, but you don't have that here. So my eye has to move a lot between the object and the horizon, and I'm trying to line them both up at the same time. And that's hard to do, even in my office chair right here. And on a rolling deck of a ship, that would be extremely difficult to pull off. Especially if you're the sun is really high up in the sky and you're all the way down here. You don't have the same thing in the same field of view at all. Another thing that I discovered about this is that it's not a linear scale at all, so that the 10 degrees of difference is this much up here, whereas 10 degrees down here is almost like 4 times the length. So that makes those sun sites down in the tropics very, very difficult with this kind of tool, because you don't have any fine adjustments down here at this range. Another major flaw of this thing is that you have to. This was used to do altitude sights of the sun at midday mostly, and you have to look directly into the sun with this with your naked eye, and that is very dangerous. And a lot of navigators messed up their eyes with this kind of tool, and some historians believe that is the origin to this trope of sailors and pirates having iPads over their eyes, because they had damaged their eyes from looking into the sun with this kind of tool.
Wow,
So,
really?
Yeah.
Huh.
Yeah.
That's super cool.
Yeah,
Not cool for them, but I never heard that. Man, August, your little recording studio there is putting me to shame. Jeez, you have so much cool stuff in the background. It's distracting.
Yeah, I've been putting some work into this. Just some sort of gathering up some different family heirlooms. This nice little sailing boat It's from my grandparents and a little globe, and yeah, it's nice and cozy in here.
So cool. So is this a good time to tell the Robin Knox Johnston Astrolabe story?
Yes, absolutely. Now, the Astrolabe is sort of halfway in the sort of evolutionary family tree. I'd say halfway between the crossstaff and the sextant, and I'll let you take that from here, Andy.
Yeah, so when I interviewed Robin Knox Johnston a couple years ago for the podcast, he was first of all the most difficult interview I ever did because I was so intimidated just being around him, and I'll bring myself back up on screen here. But he was really interested in history, and he really got going in the interview when I kind of asked him, what are you really interested in talking about? And he got going on history. And back in Columbus's day, there was all this speculation by anthropologists over whether or not Columbus was actually a good navigator or whether Columbus was just lucky in where he wound up. And back then, he would have been navigating using an astrolabe, like August said, was kind of a high-tech cross-staff or a rudimentary sextant. So Sir Robin kind of was frustrated with the fact that all these armchair scientists were speculating on the accuracy of an astrolabe while never having actually tried one at sea on a boat. So after his round-the-world voyage on Suhaili, he went back across the Atlantic. I think this would have been in the 90s. On Suhaili alone, and the only navigational tool he had was an astrolabe, and he wanted to see, using this in reality, could he find his way across the Atlantic. And I'm going to summarize. I have a quote to play you. I'm going to summarize the context of this, but basically, Columbus was 4 degrees of latitude in error when he landed in San Salvador. And Robin Knox Johnston speculated that he actually knew where he was and knew that the error was there, but it was a political move because the country of Spain had paid for his voyage in the first place, and the way they had drawn the lines for exploration of the New World, if San Salvador was under this certain latitude, it would belong to Spain. If it was over, it would belong to Portugal. So Knox Johnston theorized that Columbus fudged the numbers in order to put this territory with Spain, and within a year of that claim, they changed the number from a latitude to a longitude. So they adjusted it because nobody wanted. Knox Johnston's theory was that nobody wanted to figure out Columbus actually knew where he was and had fudged it for political reasons. But anyway, I'm going to give you a little quote here of Sir Robin. I'll try and share my screen here, talking about using an astrolabe and why he thought it was important to use it in reality as opposed to just sitting behind a desk. And let me see if I can focus the screen here. August, can you see that now full screen?
Yeah, that's
Awesome.
looking good.
So this is just an image of Robin and I talking when we did the interview, and here's the quote about the astrolabe.
Well, it goes back to the ancient Greeks, and it's basically a circle with a lever called an adelaide pinned to the middle. And you turn it round till it lines up with the sun, and then you can read off the angle of the sun. So it will work out a latitude for you, providing you know the movement of the sun. But it was interesting to know how well you can navigate with that. And everyone said, well, not very accurately. In fact, you'd be remarkably accurate, considering a degree, 60 miles, about a millimetre. You can gauge it pretty accurately. And by depriving myself of anything else and just using that, I forced myself to discover things about using it, which I'd never have found if I'd sat at a desk. Blackening the reflective surface with candle smoke showed up, a little pin of light showed up so much better. They'd have done that. They had that available. Wouldn't have found that out if I sat at a desk. And people had tried using an astrolabe, but not practically on a voyage.
Okay. Yeah.
That's where I won out. And I learned a great deal. But it was much more accurate than we thought. What I was interested in was the fact that he claimed that San Salvador was north of 28 degrees north, which was the boundary the Pope had decreed between the territory that could be claimed by Spain and the territory that could be claimed by Portugal, when actually San Salvador's 24. Therefore should have been in Portugal's. So why was he claiming that? Obviously to claim it for Spain. It paid for him to do this trip. He's Italian. And I thought, what was he up to? And you read his diary, and he's claiming he's checked this and everything else. Was he just incompetent as a navigator, or being much more political than we think? I think he may have been being more political, because within a year, the Spanish went to the Pope and said, can we change it round? So it's now a north-south line. And that is why, to this day, Brazil speaks Portuguese and the rest of South America speaks Spanish.
So there you have it. Robin Knox Johnston, the anthropologist. I thought that was really, really neat story that he shared with me there.
That is really, really cool. Yeah.
And he had mentioned earlier in the interview that he, by using candle smoke to darken the mirrors on the Astrolabe, that was a technique that they would have used back then, again, for the eye patch thing that you talked about, to not damage their vision. So really interesting, and all the cool, crazy things that Sir Robin Knox Johnston has done, that particular voyage is kind of forgotten to most of us. Didn't even know that happened, because off he goes across the Atlantic by himself to prove Columbus knew where he was going.
Yeah, that's fantastic. I mean, he's got a long, crazy resume, so I guess it's sort of easy for these things to get lost.
So, August, I wanted to transition into my kind of spiel about some of the practical aspects of Celestial, but August got to show you guys his sextant. I want to show you my sextant. I keep it on my forearm. That's actually a tattoo of the actual sextant that is, I guess, yours now, August, on Eastbjorn. It was a Tamaya sextant that I had, the one we used to navigate to Bermuda with. And you can't see it here, it's a little small, but I actually even have the serial number on it. And August, I don't know if I ever asked you this, do you know the significance of where the sextant is set right now in the tattoo? Because it was deliberate.
That is, you told me the story, and I was blown away by how awesome it was. I think it's what the... No, you tell it,
So it is set, and this required a bit of thought on my part, but it is set at what the sextant would read if I were standing at the latitude of Stockholm at 59 degrees north and getting a sight on the star Arcturus, because that was the name of our first boat. So if you're standing at 59 north and aiming the sextant at Arcturus, that's what the sextant would read. And that's a question for you guys out there. If anybody knows the answer, what does my sextant actually read? I'll give you a virtual high five if you can tell me what it actually reads, because there's a little bit of work that you got to do to figure that out. And the hint I'll give you is that, as August mentioned, the sun's declination, or its latitude, changes seasonally. The star's declination, because they're so much further away from the Earth, does not change. The stars have a fixed declination. And incidentally, another hint for that question, Arcturus would have been the zenith star of Hawaii. So the Polynesian navigators, if they were trying to get to Hawaii and didn't know how far north-south they were relative to Hawaii, if they sailed such that Arcturus was directly overhead and turned either east or west, depending on where they were, they'd wind up in Hawaii, because Arcturus always is directly overhead of Hawaii. It shares Hawaii's latitude. So another interesting aspect of kind of how you can use celestial for natural navigation. So I'm going to grab my globe for a second here, and I'll be right back.
Cool. Yeah, those Polynesians, they really knew what they were doing. It's really amazing stuff.
All right, so here we go. This is how I talk. This is how I give the beginning of all of my workshop lectures. And every time I do it, it's slightly different, but this is the gist of it. So what do we need to do in order to actually navigate using Celestial? I like to tell people that you don't ever need to actually navigate using a sextant to gain confidence as a navigator by understanding the concepts of Celestial. So I'm going to do a little bit of review here, because I think there's a couple light bulb moments that with latitude and longitude that will make you a better navigator in general. And I have a couple of screen shares I'm going to show you. But August, I'm going to use you as kind of an audience proxy, because the way I like to teach this is by asking leading questions and see if you can answer them. So just follow along with me here.
Fire
so
away.
August, do you know how latitude is derived? Like, what is latitude actually? Can you describe how it's derived and why latitude is what it is? If you can't, I will do it for you.
Cool. No, I should know that very well. Latitude is, I feel like having pen and paper for this, but sort of the angle. If you have the Earth as a great big circle, and
I actually have I have a visualization of this. I'll bring up on the screen. So keep talking.
Okay, cool. So the angle on the sort of surface of the Earth in relation to the center of the Earth would be your latitude. So
to clarify that, I'm going to interrupt you here for a second because I have this visualization on the screen. Can you see this on the screen?
Yes.
So we're looking at a cross section of the Earth. So imagine you're looking at the Earth cut in half on any meridian line, which incidentally is called a great circle. So you cut it in half along any line of longitude, and we're looking at it from the inside out. So you've got 360 degrees in the circle, and each line of this if you look at this as a bicycle spoke, each angle that goes out to where the surface of the Earth is, that's an angle created in relation to the equator, and that then dictates what the latitude is. So for example, 23.5 degrees north on the surface of the Earth corresponds to where that angle made between the equator and this bicycle spoke intersects the surface of the Earth. So the confirming question I always ask here is, would a degree of latitude, let me back up for a second, on the surface of the Earth, 1 minute of latitude is equal to 1 nautical mile. That's something that we just decided. It's a way to break it down. So 1 nautical mile is 1 minute of latitude. There's 60 minutes of latitude in 1 degree of latitude. But if we went to the moon, you could still use latitude and longitude, and they do use latitude and longitude for like the space program on the moon to identify coordinates on the surface of the moon. But you'll notice that they don't use nautical miles, because a nautical mile on the surface of the moon would be a lot shorter by the same definition than it would be on the surface of the Earth, because the moon has a much smaller circumference. If you look at this circle inside the circle here, if you know, this is not to scale clearly, but if this smaller inner circle were the moon and the outer circle is the surface of the Earth, the same rules apply to create your lines of latitude on the surface, but the distances between them are much, much smaller, and that's down to the circumference. So the space program uses the metric system because a kilometer on Earth is also a kilometer on the moon, and so on and so forth.
That is really, really cool. I didn't know that about the moon. That's fascinating.
Yeah, there you have it. So so the follow-on to this, you know, I picked that 23.5 degrees latitude for a reason, because 23.5 degrees north, August, what is the significance of that latitude?
Tropical Cancer.
Correctamundo. So the tropics, people tend to associate the tropics with palm trees and sandy beaches, but the tropics are actually specific lines of latitude on the globe. You can see it's represented by a dotted line in the north, Tropic of Capricorn in the south. They're not just arbitrary lines where it's warm most of the year. Those lines are defined by the movement of the sun's position throughout the course of the year. So if you imagine, one thing that you have to do with celestial is pretend that the Earth is the center of the universe and is fixed. And we call this the terrestrial sphere. And then all the stars and the moon and the sun and the planets are embedded in, if you can picture this being inside of a giant beach ball. The stars, the sun, the moon, the planets are all embedded on the surface of that beach ball, and we call that the celestial sphere. In reality, we know that they're all different distances from the Earth, but for intents and purposes for celestial, imagine that they're all embedded in one plane called the celestial sphere. Because the sun is closer to the Earth, and because the Earth is not standing straight upright, we have different movements of the sun's position on the surface of the Earth. So you have movement in longitude, as August described, through 24 hours. That's actually the rotation of the Earth. In celestial, we say the sun is going around the Earth, but that's actually not what's happening, but you get the picture. And throughout the seasons, the sun travels north and south. So right now, it's May 3rd. We just crossed in March the vernal equinox, the spring equinox. And the word equinox shares a root word with equator. So on the spring equinox, that's when the sun is exactly over the equator. And the next day, it's going to start moving north and moving north and moving north. It's going to move north until what date, August? When does it reach its max?
Oh, got me.
June 21st.
Not sure.
June 21st.
Right.
So on June 21st, the sun is going to go all the way north to the Tropic of Cancer. And that's as far north as its latitude is going to get because, and where does that 23.5 degrees come from, August? Because the Earth doesn't sit straight, it's tilted. And guess what that tilt is? 23.5 degrees. So over the course of the year, as the sun goes, if my head is the sun, as the Earth goes around the sun, and being that it's tilted, at different points of the year, it's going to be over the equator or over the Tropic of Cancer or over the Tropic of Capricorn. And those latitudes that define the tropics are actually defined by the limits of the sun's travel north and south throughout the course of the year. If you were to graph that on a globe, it would look like a sine curve. So that's, a lot of this stuff you take for granted is actually based on reality. The other side of that, August, closer to where you are, is that same 23.5-degree tilt also defines the Arctic Circle and the Antarctic Circle. Because if you take 90 degrees from the North Pole and subtract 23.5, guess what? You come to 66 degrees 30 minutes, which is the Arctic Circle. Same thing from the South Pole. So my point with this is all this stuff is based in reality. None of it's arbitrary. Latitude isn't arbitrary. The way the sun's declination changes it's all based on the whole movement of the universe stuff. So understanding that is the first step to understanding how you actually navigate on Celestial. To fast forward a little bit here, the way modern Celestial Nav is, I think somebody actually asked this question. This is the most, so this is Garrett answer. I'm going to answer this one. He asked, what has changed in Celestial navigation with modern technology, if anything? So August kind of teased this in the beginning, but modern Celestial Nav, the way I teach it, the version I teach, is based on the site reduction tables called HO249. And they were designed for air navigation. Because back in the days of, I dropped my globe, back in the days of sailing ships, it didn't matter how long it took to work out your position because the ship wasn't moving that quickly. But at the advent of the aviation age, as they started doing these trans-ocean flights, and they navigated the same way. If you were flying over land, you could use landmarks, just like we use in coastal navigation. But once you got out over the ocean, you were kind of lost. You were using dead reckoning. So, of course, they took a sextant up into the cockpit, and they used what was called a bubble horizon, which is an artificial horizon, which is a good training tool for those of you that are landlocked. But they'd actually use this in a plane because you're so high off the horizon. And they developed tables that were quicker to use. So you could get, from the time it took you to get a site until you had a line of position from that site, it moved the process along a lot faster since, of course, in an airplane, you're traveling a lot faster. So that's what we use with modern Celestial Nav on boats. That's what I teach. And you lose a little bit of accuracy in using those tables, but the accuracy that you lose it's basically on the deck of a rolling ship at sea, even on a small sailboat where you can get in a good position, you're going to be way off just from human error using the sextant. It's a negligible accuracy that you get by using the air navigation. So we use site reduction tables for air navigation. And where I was going with this, the way that this works, the way that the site reduction tables work, and this is the biggest leap in Celestial, and I usually take about 2 hours to get us to this leap, but we didn't have that time today. So if you take one of our workshops, you'll have a longer lead up to this. But the way it works is the tables have created effectively what are calculated sextant angles for given positions on the surface of the Earth. So, for example, if you have a whole degree of latitude, so the book, you have to have a whole degree of latitude for the book to work. So 39 degrees, 40 degrees, 20 degrees, whatever. There can't be any minutes attached to it. So if you have a whole degree of latitude, and if you have a whole degree of what's called local hour angle, and to briefly explain local hour angle and Greenwich hour angle is quite simply the longitude of the sun. So that's how many degrees of longitude has the sun traveled past Greenwich. To give you an example, at high noon in Greenwich, the latitude of the sun would be 0 because Greenwich is on the prime meridian and that longitude is 0. So 2 hours later, or say 24 hours later, the sun has done a full revolution around the Earth. So we've gone 360 degrees of longitude until noon the next day in Greenwich. So each hour, if it takes 24 hours to do that 360 degrees, each hour the sun is moving in a westward direction 15 degrees. So again, if it's 2 p.m. in Greenwich, and this is why you always use Greenwich Mean Time, incidentally, but 2 hours past Greenwich, the sun has moved 30 degrees of longitude past Greenwich, so therefore the sun's longitude is 30 degrees at 1400 Greenwich Mean Time. And obviously, because our yearly calendar isn't exact, I think it was a leap year this year, those numbers aren't exact, and that's why you use the Nautical Almanac to find an exact number, but you get the picture. So back to the site reduction tables. They use this method where, local hour angle. If Greenwich hour angle is longitude measured from Greenwich, local hour angle then is the longitude of the sun as measured from your own position. So if you're at 75 degrees west longitude and the sun is at 60 degrees longitude, you've got 15 degrees of longitude between you and the sun. And there's way more to that I won't go into now, but that's the gist. Local hour angle is longitude between you and the sun. Greenwich hour angle is longitude between the sun and Greenwich. So what the site reduction tables do is they figure out what the sextant would read at a given position so long as it fulfills these certain requirements with whole degrees of latitude and whole degrees of LHA. And then what you're doing, and I'm going to share my screen again here, you are comparing the sextant angle you got at an exact time. So if you think of it in slightly different terms, you have a couple pieces of known information and a couple pieces of unknown information. You know what time it is when you took the site. You don't know where you are. That's what you're trying to figure out. You know approximately where you are because you have a dead reckoning position. So you kind of know at least what ocean, what neck of the woods you're in the ocean. But you don't know where you are. You know what time it is. You know exactly where the sun's position is on the surface of the earth. Because the moment you take the site, like August said, you're going to freeze time. And you're going to use the Nautical Almanac to tell you at this date and exact time, literally to the second, where would the sun be directly overhead. And that is called the sun's geographic position. So you know where the sun is. You don't know where you are, but you know what time it is. And the site reduction table tells you there's somebody else, an imaginary person that I call Popeye, at a position. And the book tells you what his sextant would read at that position. And then all you're doing in modern celestial is comparing your own sextant angle to what I call Popeye's sextant angle. August, can you see this graphic on the screen here?
Yep, looks good.
So the gist of this is if my sextant reads, I'm where Popeye is here in the graphic. I'm all the way at the outside here at my DR position. If my sextant reads 27 degrees 18 minutes, and Popeye's sextant over here at the assumed position reads 40 degrees 10 minutes, and it would never be that far apart. This is just for example purposes. That means that Popeye is much closer to the geographic position of the sun than I am, and that those sextant angles are directly convertible to nautical miles. So using that 1 nautical mile is 1 minute of latitude, I can subtract the Popeye's sextant angle, my sextant angle from Popeye's sextant angle, and I can get a distance called an intercept. In this case, it's 700 miles away. If you're doing this properly, your intercept is never going to be more than a full degree or more than 60 miles. And what you wind up with is this. All you get is not a position, but you get a line of position. So what's happening here is by using simple geometry, you can figure out how far you are from the sun. And that's using, I'm not going to get into it, but basic geometry of measuring the angle of the sun with a sextant. You can figure out how far you are from where you took the sextant. And you've created what is effectively a circle of position around the sun. Your sextant would have the same exact angle at that exact time anywhere around that circle because the distance, the distance between you and the sun is the same. So what you're using with the site reduction tables is you're trying to find another sextant site that in a position where you know where that position is and comparing the two using an intercept. So that is like the first half of my celestial workshop condensed into a 10-minute lecture. But it is the gist of what modern celestial is. So to answer the question more clearly, a lot has changed in celestial because back in the days of Nathaniel Bowditch, the American Practical Navigator, that big fat book that everybody should have on their shelf at home, before the site reduction tables, you would have used spherical trigonometry to actually work out all the math to figure out exactly what I just showed you there to get a line of position. But nowadays, you can use the only math that you use using these site reduction tables is adding and subtracting. The hard part comes in keeping track of all the tiny little numbers and the fact that you're sometimes using base 60 math, which is, of course, degrees, minutes, and seconds, and sometimes you're using base 10 math, and sometimes you're mixing the two. So, for example, when we take a sextant reading, you're taking degrees, minutes and then tenths of minutes. So you've got 2 columns of base 60, and then you've got a decimal minutes instead of using seconds. We don't use seconds because you don't need to go down to that level of accuracy. You're using tenths of minutes. And most people make mistakes by simply transposing the wrong tiny little number or by doing the math wrong. But all the math that you need to know for this is addition or subtraction. And I will say, people always ask me in my workshops, can I use a celestial calculator? It's like, yeah, you could also use a GPS. So the way I do this is I use the real books because they're much more easier to reference than the PDF versions. And I use pencil and paper, and I use my worksheets. And August, I'm going to grab the book quick. If you can just tell an anecdote for a second, I'll be back in a second.
Sure thing. Yeah, I mean, like using celestial calculators is it's a really quick and easy way, but the whole point of celestial navigation, as I see it, is to be able to navigate without any electronic aids, basically. And I kind of feel the same way just about having the nautical almanac and the tables on my phone. It just feels, it's just wrong because I'm just sort of, instead of being reliant on the GPS, I'm now just relying on a different kind of piece of electronics. So I've not really gained anything from that. And yeah, it's all about the pen and paper to me, I think.
I agree with you. And if you were actually, back in the day when we didn't have GPS, then I think using a celestial calculator, if you're actually depending on it for navigating, is not that bad of a thing to do. But nowadays, we're using it more for like the romantic aspect of it. So it feels like cheating if you're using that stuff. I want to show you what I mean by the transcription errors. This is the site reduction table for air navigation, HO249. And you actually can this is a government publication. You can find it for free online. You can download this for free online, but it is impossible to use scrolling through an iPad or on a computer. But check this out. I'm going to make my screen bigger here again, August. This is your columns of numbers. So you can imagine you need to find one single number using a variety of, you're cross-referencing this table with numbers across the top and numbers down the side. But it is super, super, super easy to write down the wrong number from this simply by transcription. So what happens is, as you get better at using the books, you tend to have, there's a couple sort of self-checks along the way where if the number doesn't make sense when you write it down, you'll kind of second-guess yourself and make sure that you got the right number. And that's where, when you first start with Celestial, it's kind of overwhelming because you don't have that sort of self-check just in the back of your head because you're not as familiar with it. But anyway, that's the sort of essence of modern celestial navigation, is you're taking a site at an unknown position but at a known time, comparing it to a known site at a known position, and plotting the difference. So that's it in a nutshell, plotting that intercept and the distance. So back to my my quiz here. What does my sextant actually read? And Bill Marshall gets the virtual high five here. And maybe, actually, Garrett said he got it first. Nice steal, Bill. So anyway, both of you guys, it is 50 degrees. And the reason for that, if I show you the globe, Arcturus as a star has a fixed declination. Declination means latitude. The declination of Arcturus is, what did we say? Let me look this up, I think, so I don't mess it up. Declination of, or hang on. Latitude of Hawaii, that'll tell it to me. I think it's 40 degrees. 20 degrees, 19 degrees. So the declination of Arcturus is 19 degrees north. So if I was standing on 59 degrees north, there is 40 degrees of latitude between me and Arcturus's position on the surface of the Earth. But you have to take my sextant wouldn't read 40 degrees because Arcturus... This is hard to explain without having a whiteboard in the background, but suffice it to say, you need to take the complement of my sextant angle, or the complement of the difference in latitude between me and Arcturus. So 40 degrees, the complement of that is 50 degrees, because that makes a 90-degree right triangle. So Bill corrected himself. It is the complement of 40 degrees, it's 50 degrees. So my sextant, even though there's no numbers on it, is set to read 50 degrees because of Arcturus and at 59 north. So there you have it. So I hope you guys learned something. I want to take some questions now. August, what did I forget to say? I mean, like I said, that's half of the first day of the workshop condensed into a 15-minute chat here. But anything to add to that before we take some questions?
No, I think that was good. Like you said, it's not possible to learn how to do this in 90 minutes of a live stream on the internet. But I think it was great. I mean, that's the gist of it, really. And yeah, sign up for a workshop if you want to learn how to do this properly. So
yeah, speaking of the workshop, I put a poll down at the bottom of the screen, which is asking people if you would sign up for a workshop. So we're gonna do one of these online workshops. The idea is it's going to be 4 days, but it would only be 2 to 3 hours per day. We'd break it up. Normally we do an in-person one is 2 full weekend days, but we'd break it down into 2 to 3 hours a day for 4 days. I put a cost there. If it costs $259, would you sign up for it? And even if the dates don't work, the replays would be available. So you could buy the course. If you missed it live, you could still watch the course on the replay. So if you want to do one of those courses, just answer that poll, and we'll talk about when we're going to do that. But okay, so some technical questions. August, let's see if we have one here. So Kat asked, can you provide, she asked the precise order for adjusting mirrors, but rather maybe just give a quick technical, show people how to adjust the mirrors to take the error out of the sextant, since you've got your sextant there. Are you able to do that, August?
Yes, it'll be a little bit hard to do. What you can do is to adjust these mirrors by, you see this little knob right there? You can put a little screwdriver tool thing in there to adjust the angle of the index mirror. And you also have a similar one down here on this mirror down here, so you can adjust these. The sort of, if you do one before the other, doesn't really matter that much, but that will, and you will sort of look through the telescope for adjusting the index mirror to make sure that's all right, and you will look at the, it's a bit hard to show you, but you would look at the arc through this mirror and kind of have that line up properly and adjust that mirror to make sure they're all right. And
a key point on the adjusting the index mirror, you need to have a clear horizon. You can't just like aim it at a straight line on the wall in your house. You have to have a watery horizon to get that depth perception proper, so it lines it up right.
Yes, absolutely. And often you would just often you wouldn't adjust your index mirror every time you're out taking a sight. You would basically just check what we call the index correction, or the index error of your sextant, and that is basically you can just set your sextant to 0 degrees, 0 minutes, and just look through the telescope, adjust the micrometer drum until then you'll see 2 horizons, one in each side of the telescope, and you will adjust the micrometer drum until there is just one straight horizon like that, and you would read off the error down here. It'll usually be, just a little bit of error, and you just put that into your calculations. Just add or subtract that.
Yeah, and that same thing, people ask, like, what kind of sextant should I buy? Any sextant will give you accuracy so long as you know how much error is it from the start. So a plastic sextant needs to be adjusted far more often because the material itself changes with temperature and humidity. A bronze sextant needs adjusting far less often, but you can get accurate sights with both so long as you take into account the error inherent in the material behind it.
Yeah, that's right. This is my first sextant. I have that here as well. This is a plastic one. So it weighs 1/10 of the big Russian piece of metal, and it's not as accurate being that it is plastic, but you could find your precision to within 5 miles with this. No problem.
And the thing about the weight of that is sometimes if you're taking sights for a long time, you lose a bit of accuracy just with fatigue. Holding a bronze sextant up as you're taking a noon sight, which takes 25 minutes, you're going to lose a little bit of accuracy if you're, shaking when your muscles are fatigued by holding a sextant. So the plastic one is far easier to use over time. So it's kind of a balancing act there depending on what you're looking for. But by nature of the material, the plastic, you can't manufacture them with the same amount of accuracy. Aluminum is somewhere in the middle. and then bronze, they can tool those to be super duper precise on a bronze one.
That's right.
And Kat, also follow up. Do you have any makes, models that you'd recommend? Because I can, and because there's no reason to do this, but I sprung for a Tamaya. The new one I have on Ice Bear is a Tamaya Jupiter Sextant, which I think costs like $2,500 new. But I made a deal with Weems and Plath and traded some podcast advertisements for one. So that's the reason I got that one. The Tamaya that you have on Eastbjorn, August, I got secondhand for like $250. So Tamaya is a really good brand if you want to go all out. The Astra 3B is if you want a new aluminum one, they're like less than $1,000, I think. And the one you have there, the Davis Sextant, I think they're like $200, something like that.
Something like that. And I gotta say, I mean, this is a really cool place to start out. This was my first sextant. It was really cool to learn celestial on one of these. And then when I decided to get a proper metal sextant, I mean, I still have this and it's a great backup sextant. So these are pretty cool. And just like you said, Andy, it's usually the accuracy of your celestial fix is not due to the quality of your sextant. Usually it's the visibility of the horizon or just you being thrown about a lot. That's the limiting factor. So, yeah.
So, a couple more quick questions here I want to take as we go through here. There's a couple people asked a similar question, and I'll take this one from both Rory, my friend Rory, who's watching. Hi, Rory. How's it going? In fact, Rory, let's see if you've got a camera. I'll bring you up on screen. You can ask this yourself. It'd be nice to see you. Rory has raced with us a couple times on Eastbjorn and other boats that I've raced on. So Rory has sailed with me a couple times. So let's see if he can come on up on screen to ask this. But while he's coming up here, a couple quick ones. Is it difficult to practice when one lives inland? That's from Mark. You can it's called a bubble horizon. So it's an artificial horizon that allows you to actually get a usable line of position. You can practice the theory and the math. Hey, what's up, Rory? Rory, I'm going to finish answering this question real quick, and then I'll get to you. But Mark, again, if you want to practice, you can get like site data that was taken, and we have a bunch of site data from actual trips, and you can practice doing the math, because doing the actual sextant site is the easiest part of it. It's going through the example problems and working out, doing the site reduction, that you kind of lose that over time. So yeah, if you live inland, you can't take an actual site per se unless you have a bubble horizon, but you can practice the site reduction, which is the tricky part. What's up, Rory? How you doing?
Good to see you guys. I've been really enjoying these live streams. Cool.
Yeah, man, these are fun. So, Rory, you had a similar question to Glenn. So why don't you go ahead and ask your question?
Yeah.
About the stars. Sorry, the steering stars.
Oh yeah. Well, so my main question, the one that's on top, is just about how many sites per day you would take. Do you just do a noon site, or 2 or 3 per day, or how do you do that?
Yeah, so to answer that question, your basic, if you're actually navigating on Celestial, and this relates to somebody else asked a question about like what happens if it's overcast, if you're down in the Southern Ocean. And August, you and I are going to find out firsthand when we do this OGR race what happens when you can't take a site for 3 or 4 days. Michael asked that question. So basically, Dead Reckoning is the key to really navigating on Celestial, because Dead Reckoning, like August said, is kind of the breadcrumbs in the forest. You want to keep track as much as possible where you are based on distance traveled and time. So if I take a 4-hour watch and I leave Annapolis Bay Bridge, like Rory, when we did the Annapolis to Bermuda race, you were on that one. Our last known position could have been at that lighthouse outside the Bay Bridge. So we know where we are there. And then at the end of your 4-hour watch, you can tell the navigator, hey, I've been steering about 130 on the compass, and the log, the speed is not what's important, but the log might say after 4 hours, if we were going 8 knots, we would have done 32 miles. So the navigator then is going to measure 130 degrees on the chart for 32 miles, and then that's our Dead Reckoning position. Now that doesn't account for current and stuff, but a good Dead Reckoning log is the key to that. And when you have good conditions, you're going to take as many sites as possible, because you want to always reset your position, and you're only able to get a single line of position from any given celestial body. So your routine as a navigator with Celestial would be at dawn. So overnight, you're not taking any sights in the middle of the night because you don't have a clear horizon. It's too dark. Even with a full moon, it's too dark to get a sharp, crisp horizon. So over the night, what you're doing is you're planning for what stars are going to be visible at dawn. That's that nautical twilight. So at dawn, maybe a half hour before the sun comes up, you're going to know from the planning you did overnight what stars are going to be visible and where in the sky you're going to look for them. If you can take 3 or 4 star sights within a 10-minute window, you can actually fix your position using a star fix, because you're going to get 4 or 5 lines of position. You're going to chart them all on the chart, and where they cross is going to be your fix. So your routine would be in the morning you get a star fix. 3 is good, 4 or 5 is even better. As the sun comes up, about mid-morning, you're going to get a sun sight. That's going to be your first sun line of position. Then at noon, you're going to get your latitude from your noon sight, and you're going to advance your morning sun line to that position to get what's called a running fix. Going to do the same thing in the afternoon with the sun, and then the same thing with the stars. At dusk, you're going to get after the sun sets, but before it gets totally dark, you're going to do another star sight. So you might take 5 lines of position throughout the day, and every single time you take a sight, you're going to take 4 or 5 sights to make sure that the wave didn't knock you off on one or whatever. And once you get comfortable with it, you'll know, did I get a good sight or not? And you're going to throw out the bad ones. Or what you can do is you add them all together, add the time together, and average it out. So you're smoothing out any error in the actual sight. But it is a lot of work. And that's why, even more important in the celestial day, the navigator was not in the watch rotation. All they did was they lived and died by the cloud cover. If the sun was out, they were outside taking sights. And that's why dead reckoning is so important, because if you get a week of clouds, you only know where you are based on dead reckoning, and you can't reset that dead reckoning position until you get a sun sight. And that's where, if you go a couple days without getting a sight, you better damn well trust your sextant, because your dead reckoning is going to be off. 5 days of no sights, you're taking your dead reckoning, but when you get a line of position, it's not going to be very close to where your dead reckoning was. You might be within 50 miles, but at that point, you have to trust your sextant, because you can no longer trust your DR. And that trust aspect is the hardest aspect of actually doing celestial, because it's like, oh shit, like, do I trust myself? Do I trust my watch? Because it's all dependent on your watch as well. So that's the gist of actually navigating on celestial. It's a full-time job. Did that answer your question?
Yeah, it did. Thank you.
Cool, man.
Yeah, I was able to get latitude on the trip I did with Dennis in the Pacific with Dennis Judd, and I never got to the point where I could do longitude correctly. But I need to take your workshop still.
There you go, man. Cool. Well, thanks for joining us, Rory, and I'll hope to see you sometime if this quarantine ever lifts. I can get back to Annapolis if you guys are still around.
Yeah, exactly. Thank you.
Cool, man. Take it easy. All right. August, can you see the questions? You want to pick a question?
Let's see. Yeah, sure. We have the second top one here. How do you determine sight height when in large seas? That's a good one. That's my favorite way of doing that is to sort of get myself as high as I can on the boat. Usually that would be sort of amidships at the shrouds. Because I'll be pretty high up, so I'll be sort of above most of the waves, and that's also a very sort of stable part of the ship, just in the middle there, and I will sort of hold the sextant and wrap my arms around the shrouds, and just keep looking at that horizon until, or just looking at where the horizon would be, and then just wait for the waves to clear, basically, to give you a fine look at the horizon. And then,
sorry, go ahead.
Yeah, just like when you actually finding the celestial object sounds pretty difficult. But if you're navigating on celestial and you're doing this every day, you basically know where that celestial object is going to be. So I'm gonna set the sextant to, I know that, okay, yesterday I observed the sun at 40, and today I've just had it headed a little south, so I'm just going to add a little bit to that, and then I'll look, and I'll be pretty close. I could pretty much see the sun in the telescope just from the get-go. So it's not as hard as it sounds, really.
Yeah, and the other part, I'm not sure if Glenn was meaning what you said or the determining height of eye, but basically your height of eye on a sailboat you can always assume is about 9 feet off the horizon. Or sorry, not off the horizon, off the water. So all the books are calculated, all the numbers are calculated assuming you're at eye level in the water, like literally floating in the water taking your sight. But because you're up on deck, you have to account for that. That's called height of eye or dip, and you don't make any adjustment to that if you're in big seas because you're still 9 feet off of the top of that wave or whatever. It's about what August said, making it hard to see the horizon in rough seas, but your height of eye is not going to change in rough seas. It's not going to change appreciably. You're going to lose a bit of accuracy because it's rough, but you're not going to change your height of eye. So Glenn, I have another good question from Glenn here. Let's see if Glenn wants to come up on screen actually to ask this one about the stars. So Glenn, if you want to come up on screen, just answer the prompt I just sent you. If not, no worries. I'll just answer it for you if you don't have a camera or whatever. But if you want to come on up, just follow the prompt. All right, he said accepted and connecting. While we're waiting for Glenn, Ken asked, can we pre-register for your online celestial class? Yes, once we get the dates set. Hey Glenn, how you doing? I can see you. We can see you. Glenn, just ask your question. All right, let's see. Glenn. All right, Glenn, I'm going to say bye. Wave bye. Bye, Glenn. So I'll answer. We got to see Glenn anyway. I'll put a face to a question. Glenn asked, I recently listened to Cape Horn to Starboard by John Kretschmer. Incidentally, John is who taught me Celestial in the first place. I went to one of his workshops in 2007. And Glenn says he referenced steering by a star or steering by the stars, and he asked if we have any light on what that actually means. So another way that I think using the concepts of Celestial without ever getting the sextant out is cool is this kind of steering by a star thing at night, because you'll find offshore at night when there's no reference point, all you're doing is steering by a compass. If you've not done that, it's really difficult to maintain a compass heading just steering to a compass that's lit up by red light and is right in front of your face. You go cross-eyed. So if you can line up the boat's compass course where you want to go, there's oftentimes, especially in the tropics, a star kind of, or a constellation that is on that same compass heading that you can use to point the bow at a star instead of staring at the compass. And then obviously the night sky is moving throughout the night, but over the course of a 3-4 hour watch, it's not going to move that much, and you don't have to hit the number exactly on the compass. You're going to hit it within 10 degrees of either side because of the waves and the error on steering. But you can use a constellation if you line one up with the compass heading, and now you're steering to a star instead of by the compass, maybe occasionally checking the compass heading to make sure you're still aimed at the same star. But we do that all the time, August. I mean, I'm sure you do too.
Absolutely. Yeah, I mean, it's so much more comfortable to be looking at a star than at that compass. And especially for people who might be prone to seasickness, it's a lot better to be watching that star and what you can of the horizon than sort of be staring down into the compass. So it's, yeah, that's a really good technique.
So Rob asked, is the worksheet you use publicly available? It is. You guys, since you registered for this, you provided your email address. I will email out a PDF version of the worksheet for everybody, but I'll show it to you right now and kind of walk through it because somebody else asked walking through an actual site. So I'll take a second. Those of you that are interested in the technical details of this, I have, let me see, I have my sunsight reduction worksheet. Now, I feel very strongly about worksheets because most of the worksheets you find in books that are published are crap. I've developed this one that I made myself over the last 10 years I've been teaching this course, and I think this one is much easier to use than the ones that you see published otherwise. So like I said, I will email this to you guys. I think I have a link on the website, but anyway, I'll send you a PDF of this, everybody that's here in the workshop. But to walk through the process of actually taking and reducing a site, August, you got the worksheet on your screen there just to confirm?
Yep, looks good.
All right, so modern celestial using HO 249 is divided into 4 parts. I divided into 4 sections. So section 1 is your sextant observation and corrections. Section 2 is figuring out the sun's geographic position, and in parentheses, that data comes from the Nautical Almanac and the time you took the sight in Greenwich. Step 3 is referencing table HO 249, so that is going to give you what Popeyes sextant would have read, or what the calculated sextant would have read at the assumed position, which we didn't get into that. And then step 4 is plotting all this on the worksheet, which I showed you earlier, and I'll go back to that in a second. So if we go through this step by step, step 1, sextant observation and correction. So there's a lot of factors that make your initial sextant sight not accurate. First of which is dip, that's height of eye. August talked about index error, so is there any error in your sextant? One benefit of correcting your sextant is it's one less calculation to do. If your index error is 0, then you have a 0 on this line, and there's one less piece of math to do. Height of eye on a sailboat is always going to be about 9 feet, and that is going to give you a minus 3 minutes correction. So height of eye, as long as you're on a reasonably sized sailing boat, it's almost always going to be minus 3 minutes. And then the last correction is refraction and semi-diameter. So that's actually 2 corrections that the Nautical Almanac works into one. And refraction is simply the bending of the light of the sun as it travels through the atmosphere. So the lower on the horizon the sun, the higher the refraction, because it has more atmosphere the light is traveling through. It's why the sun looks squashed on the horizon at sunset. Semi-diameter is the fact that when you take a sight, August was describing this earlier, you're actually bringing the lower edge of the sun down to the horizon. The sun is large enough in your field of view that it's a disk as opposed to a point of light like a star. So because all the books are based on the center of that disk bringing to the horizon, you can't do that because you can't pinpoint the center of the sun when you're looking at it through a scope. So you use the lower edge, which the books call the lower limb, but then you've got to correct for that. So those 2 corrections are given to you on the inside cover of the Nautical Almanac, and they change based on the time of the year because sometimes the Earth is closer to the sun, and therefore the sun's disk, the diameter of that disk is actually larger when the Earth is closer to the sun. It's measurably larger. So you have to look in the right column, but that's your last correction. So part 1 is simply taking the sextant sight at a given time and then correcting the sextant. So the bolded box at the bottom, H sub O, that's your actual useful number. That's the corrected sextant angle based on those different corrections. So that's what your goal is from part 1, is to figure out what your sextant, a usable number. Part 2 does not involve the sextant at all. This is just from the Nautical Almanac. So this is related to time. You're going to freeze time the second you took that sight, and then the Nautical Almanac will tell you, based on declination and GHA, that's another way of saying latitude and longitude, where on the surface of the Earth would the sun be directly overhead. So that's all you're doing in part 2 is pinpointing the geographic position of the sun or whatever celestial body you took the sight with. From that information, you're then creating what's called the assumed position, and this is the biggest leap in this type of celestial. You're figuring out where Popeye was, and I'm not going to go into how to do that, but it's pretty easy it's based on your own dead reckoning position, which you're going to write at the top of the worksheet, and it's based on the time that you took the sight. So step 2 has nothing to do with the sextant. It's all from the Nautical Almanac. Once you've established Popeye's position, that's why we bolded this box down here, you're going to use Popeye's latitude and the local hour angle of the sun. So that's how much longitude is between you and the sun. You're going to use those 2 figures to reference table HO 249. What you're trying to accomplish from referencing 249 is what would Popeye's sextant have read at his position. And then from that, figuring out the intercept. And the intercept is the difference between your sextant and Popeye's sextant. And then the last part is taking that intercept and plotting that on a chart. And that is modern celestial in a nutshell. And I'm going to show you that. I'll show you that plot example one more time here. Ultimately, when you go through that worksheet and you get to the end of the, let me make the screen bigger there. When you go through that worksheet and you take, the other part of this is a universal plotting sheet. So look up universal plotting sheet. I don't have to explain that now. But ultimately, you're going to wind up with a plot on a chart that looks like this. And that gives you your line of position. I can't make that big screen for some reason. Anyway, your line of position effectively is a tangent to that original circle of position that you got from before. So 4 steps to get to this point, and all that work only gives you a line of position. It doesn't actually give you a position unless you take more than one site at the exact same time, and that's what I mentioned with the stars in the morning and the evening. That's why that's so important, because you can get a fixed position as opposed to just a single line of position. So that sounds like a lot, but I can say once you practice this, you can go from taking the site. So once you get the site, which takes a bit of time till you get yourself in position, but all that work from the worksheets down to the plotting, I can do in about 10 minutes. And I no longer even need a worksheet. I've done this so often that I have that worksheet in my head and I can just use a scratch piece of paper. So it sounds daunting, but if you practice it a lot, you can get pretty quick at it. And that's how we do it. So hopefully that answered your question. That was a little bit technical, but Rob, I hope that answered your question. I think that was Rob that asked that. Let's see. We'll take one more question. August, you want to pick the last question? We're right at 90 minutes now. You and I could talk about this all night long, but it's 10:30 at night here in Europe.
It is, yeah. No, we have a lot of requests for doing some of the maths behind this. I think that's a bit too big for this. I think we'll need to do the workshop for that. But there is one question here by Thomas Sætre. He sounds Norwegian, so I'm gonna pick that one. He asks, or should we try to bring him up on screen?
Yeah, sure. This is a great one because we both Thomas. I know. I think Thomas was either supposed to sail with us or has sailed with us, or signed up to sail with us, or his name has popped up a lot. So sorry, Thomas, for not knowing why I know your name, but I know your name for what that's worth. Yeah. So let's see if he wants to come up on screen. And this is a great question because it goes back to the time thing, which is a really cool part of this.
Yeah, it's a great question and a good sort of opportunity to talk some more about time, which is
so I guess really cool. Thomas doesn't have a camera or something, so we'll just answer it. Thomas asked, I'll ask the question, August. Okay. Thomas asked, where is it here? How accurate should your watch be? Say you're using a mechanical watch that might be off by several minutes at the end of a crossing. Great question. And before I let August answer this, the challenge with creating a timepiece back in the 1700s was not the accuracy of the watch, but the consistent inaccuracy of it. So August, I'll let you explain what I mean by that.
Yeah, exactly. So the thing is that you need an accurate watch. A watch that is several minutes off is going to be yielding very unsatisfactory results because, just like you said, Andy, the sun is moving around the entire circumference of the Earth every 24 hours. That is 15 degrees of longitude every hour. It's 900 knots, and it's 15 nautical miles every minute. So that gives you an idea of how important those seconds are when you're trying to determine your longitude.
4 seconds is 1 mile of error.
Right. So that is so if your watch is off by several minutes, that is going to provide a lot of problems for you. But then, as just like you said, Andy, if that inaccuracy is consistent, if you know that my watch slows 1 minute every week, you could just put that into your calculations and you could work with that and you'll be fine. If you don't know that, you might be better off just using celestial techniques from before people had accurate watches and keep running down your latitude and have your radar on.
Exactly. And back in the day, and even now, you can still buy a modern watches for celestial are called chronometers. So to buy a good chronometer, they use them. They're quartz now because that's far more accurate than a mechanical watch. But a good chronometer, I think Seiko makes one. They're like $2,000. They're really expensive because they are calibrated to such accuracy that you're going to have that precision that you need because 4 seconds of error is 1 nautical mile. Incidentally, if you go on eBay, when they take an old ship that's no longer in service, like a modern ship, like a steel ship, container ship, whatever, when they go to get broken up for scrap. They send them to India, they drive them up on the beach, and they take them apart for scrap. But before they cut them up for scrap, the Indian guys that working there go on board the ship and take anything of value off of it, and they stick it on eBay. So you can find all sorts of cool nautical stuff from these ships. You can find sextants, you can find survival suits, you can find chronometers, you can find all this super, super cool stuff. And some of it they've like modified to make it useful as like a household item. I don't have it here, I should have brought it up, but we basically bought just recently a set of 5 clocks. And on a ship, the clocks would have been wired into the ship's electrical system so that as they transferred through time zones, you could change the clocks in every single cabin by changing the master clock in the bridge, and that would then change all the slave clocks that were connected to it. But these are really neat clocks that actually existed in ship cabins, but what they've done is they've taken them off the ship and they've put just a simple battery-powered quartz mechanism behind the clock face. So we have 5 clocks now that we're going to put on the wall downstairs that are going to show one's for the time for Ice Bear, one's the time for Eastbjorn, one's going to be the time for Sweden, one's going to be the time for the U.S., where my dad is, and the last is going to be the time zone for New Zealand, which is where Mia and I met. So, and they were not expensive. We got 5 clocks for like, it was like $100 or something, and just all kinds of cool nautical stuff from these Indian guys on eBay. So check that stuff out. Cool. I think that's it for today, August. This, like I said, you and I could talk about this all night, but both of us need to go to bed at some point. And Thomas says he is Norwegian, so there you go, August.
Nice, Thomas. Good seeing you.
Cool. Well, we're gonna put up the replay to this, so if you want to go back and revisit some of this, I'll also try to remember to email you guys the PDF of the worksheet, and as well, there's a couple articles that I wrote over the years that kind of summarize this stuff on paper. So if you want, that could be useful. And check us out again. Our next live stream's on Tuesday, where we're going to be talking about history, the captain of the Pride of Baltimore, Jan Miles, as well as Jen Kay, the captain of the schooner Woodwind. So check that out on Tuesday. Thanks again. If you thought you learned something from this, send us a few bucks. And otherwise, we'll see you next time, and we'll let you know when the Celestial Workshop goes live. August, you and I need to talk about dates for that.
That's right, yeah. Yeah, no, this has been super fun. Thanks to everybody who showed up. It's really cool. So many want to hear us talking about this stuff. I love this. This has been a lot of fun. So thanks a lot, guys.
All right, August, we'll talk on Tuesday for the next one.
Will do. Looking forward to it.
Hold fast, everybody.
Hold fast.